Okay, so thank you all for coming. My job tonight, I guess I drew the short straw, right? So even though I'm an expert in algal genetics, I'm not going to tell you anything about that. But because this is, as the Chancellor said, a MOOC, a massive online open course, we have to have an introductory talk about energy and its consequences. And I'm particularly, I guess passionate maybe is the word, I don't know, annoyed by what I read in the newspaper and what I see on TV. And so at least half my talk is going to be to try to put in perspective just where we sit in energy today. Do we have a slide changer? Oh, it's here. Okay. All right. So let me start with this. I guess we have to start with the basics. This is an introductory to energy talk. So let's start with the basics. What is energy? Energy is the capacity to do work. Okay? And work is force multiplied by distance. So you will all recognize there are lots of different forms of energy. Chemical energy, the most common one you see all the time. This can be gasoline for your car. This can be food. Solar energy. This drives photosynthesis, but it also drives photovoltaics, right? It keeps us warm. Mechanical energy, this happens to be a ride, but it could be a car. Nuclear energy and electrical power, okay? So all of these are different forms that we commonly see every day, but the most important thing that we have to understand is that the first law of thermodynamics has to be followed. And what that says is energy can neither be created nor destroyed. It can only be transformed from one state to another. So what does that mean? What that means is that we do not produce energy, right? We can't make it. What we can do is we can mine it if it's fossil fuel. We can pull that out of the ground. And then we can burn it and we can convert that chemical energy into mechanical energy to drive a car or fly a plane. Okay? We can certainly convert solar energy into food or into electricity, all right? But those energies already exist, right? Where does our energy come from? Surprisingly, most of it comes from fossil fuel, about 85% of it, all right? We do get a fair amount from combustibles, right? This means wood. It also means dung in many parts of the world. You burn that for cooking or burn that to stay warm, right? We get some from hydroelectric and a fair amount from nuclear, but clearly most of it comes from these three, right? And these are certainly the things that impact us greatly. And as we'll talk over the next, 12 lectures over the next 4 weeks, right? The mining of these things, the processing and the burning of these things has significant consequences. I'll talk a little bit today about what I think some of the most important consequences are of this, which is actually not in transportation, but it's rather in food and food production. But next week we'll also talk about the consequences this has on the environment in terms of climate change. And the week after that we'll talk about the economics of this, right? Because for large parts of the world, the economics of energy are what impacts their lives gravely, all right? And then the very last night, we're going to talk about food and food security and water, right? All right, but here's an important concept that we also have to understand, right? And that is that there's a difference between energy and power. So oil is stored energy, right? It is potential energy. We can burn that. Power, which is electricity, is produced and delivered for transmission for immediate use, right? We all obviously understand this. If you go out and have gasoline in your car, you understand that that's energy, and anytime you choose to go out and turn that ignition, right? As long as your car's in good shape, it'll start and you can drive, right? That is very different than electricity. Electricity, we take fossil fuels primarily, a little bit of wind and solar, but primarily fossil fuel. We turn that into electricity, we put that on the grid, and it has to be used by somebody. If it's not, it simply dissipates as heat. So there's a big difference between these two. Obviously, for transportation, these are wonderful things that we have fuels, all right? So they're not completely interchangeable. We think about them as interchangeable, but for many things, they're not, right? Okay, so why is energy so important, right? Obviously, we use it in every single thing we do. But for myself, when I really started to look at energy about 6 or 7 years ago, I was shocked by some of the numbers on this, all right? Today, energy production in the world is $5.8 trillion, with a T, trillion, all right? As I'll show you in a minute, food and fuel are really just two different parts of chemical energy. In fact, we take a lot of our fossil fuel and turn that into food. Chemicals, you'll recognize, clearly come from fossil fuels. So if you add all of these things up together, all of those parts of energy actually equal about 70% of the total commerce on the planet. Just to put that in perspective, here's pharmaceuticals, right? We think of the pharma industry as enormous here in San Diego. It's only about $650 billion total. Now, that's not all medicine. If you add in all medicine, all surgeries, all doctors, or everything else, that number goes up a lot. But if we just talk about the physical properties of it, right, just what is bought and sold in that, it is a fraction of what the world's energy market is. And that world energy market, as the Chancellor said, is growing incredibly fast. Not so much here in North America and not so much in Europe, but in what we call the developing world, in China and India. It's growing much faster than their populations are growing. Okay? Why is it growing much faster than that? And what's another reason that we continue to consume more energy? Is this slide, I think, is very interesting, right? What this plots is gross domestic product per capita. So on average, how much wealth any individual in that country, how much you earn, okay? Against energy consumption per capita. And here we are up here, the United States, the wealthiest country on the planet, and also the largest energy consumer. Now, some countries, like Canada, consume a little more energy than us. It's a little colder up there. Distances are a little longer. You have to drive farther. They also have more energy than we have. So they don't have to quite conserve it as much. And their GDP isn't quite as high, so they consume a little more energy and a little lower GDP. Here's Japan. They're a little more conservative on their energy than we are. They tend not to drive cars. They live in smaller buildings and tighter confines. So you can certainly be different places upon this graph, depending upon sort of the efficiency of how you live. But the most important thing is that if you want to increase your gross domestic product, you do that by increasing your energy consumption. So if you're one of the countries down here and you'd like to be one of the countries up there, you do this by increasing energy consumption. So the reason that number is growing so quickly, the reason that number is growing 40% is because those two little dots right there are China and India. 2.5 billion people, 1/3 of the population on this planet. And they want to live the same way we do. They want to live in a nice house. They want to have a nice car. They want to be able to drive. And in order to do that, they're going to consume the same amount of energy we are. So as their wealth goes up, their energy consumption is going to go up. So this is going to continue to increase at a very rapid rate. Okay, so we talk about it, you know, you'll see in the newspapers, oh, we can get electric cars, we can think about different forms of transportation, but why is fossil fuel, why are liquid fuels still so dominant? And why do we still use them? Because they're actually really wonderful things, right? They were designed to be fantastic storage of energy. And so this is energy density of transportation fuels. And here's gasoline and diesel, this enormous British thermal unit. So this is the energy content per liter is enormous. Here's lithium-ion batteries, okay? That's an electric car. It's not that electric cars don't work. It's that you can only store a very small amount of energy inside those batteries. Some of you know this because if you get a car, you're limited on how far you can drive it before you have to charge it up again. If you have a gas tank full, right, with 16 or 20 gallons in it, you can go hundreds and hundreds of miles on this, because the energy density is so high. So they're actually fantastic sources of energy, right? They're a fantastic resource. The other thing is they're actually cheap. So we complain about gasoline. We say, oh, it's $4 a gallon. How can that be? You know, we demand that it only be $2 a gallon. But in fact, we pay outrageous sums of money for other things. I mean, here, I picked Fiji water here at $7.15 a gallon. Lord knows what a Starbucks coffee would be per gallon if I put it up there. Some of those fancy things, I'm sure, are well over 25, right? This, at $4 a gallon, is still only 60 cents a pound, right? That's cheaper than potatoes, that's cheaper than rice. That is literally cheaper than anything you can get on the planet except dirt, right? The other thing, that this enormous energy density, so 1 gallon of gasoline has 116,000 BTUs. That is equivalent to about 108 slices of pizza, right? So if you had to go out and buy the same number of calories as in a gallon of gasoline, it would cost you about $217. This is why fossil fuels are still used. This is why they're still going to be used in the future, right? Because there is still a fair amount on this planet. Although we'll talk a little bit, there's not quite as much as maybe you've heard recently. So today, in the United States, we consume about 300 billion gallons of fuel every year. About 19 million barrels a day. This is total consumption of the world over the last 25 years. Right? Today we're just a little bit under 90 million barrels per day of energy consumption. And what you can see is, by and large, these countries here, which is Asia and Pacific, they're going up pretty quick. Many of you may know that in North America and Europe, we've actually declined over the last 4 or 5 years in our energy, in our petroleum use, mainly because we've gotten more efficient in our automobiles, something called the CAFE standards. It was a requirement that cars become more fuel efficient. We've also become more clever about insulating our houses and getting more fuel efficient in our buildings, all right? But we already live at a very high standard of living, so we can afford those efficiency increases. These guys don't live at a high standard of living. This is by and large, this increase is electrification in India and China. This is the power plants that are going into India and China so that they can have electricity, so that they can read at night and maybe air condition their buildings, all right? So this number is going to continue to go up. Here's just one really good example of it. This is actually a picture from the freeways in Beijing in 2009. And I had been there 10 years previous to this, and at that time there was a huge number of bicycles and mopeds just everywhere. They just dominated the streets. And when I went back in 2009, this is what it looked like. All the motorcycles and mopeds were gone. And they had been replaced by these brand new cars. Maybe it's a little hard to tell from this picture, but all of the cars are brand new. And in fact, in 2010, 11 million new cars were sold into China. About the same number that were sold into the United States. Although in the United States, that's about a steady state. We retire about 19 million cars per year, and we put about 19 million new ones on the road. In China, these are all new cars. So this is simply a plot of the number of automobiles that are coming. Here's the increase in the world. Here's US, we're at steady state. In 2011, worldwide number of cars surpassed 1 billion automobiles. And this number is going to continue to go up.